today we are going to finish section 4.2 and also do section 4.3. We're going to talk about exterior angles for triangles and their remote interior angles. When you have a triangle and you extend one of the sides, you create an exterior angle. In this example, angle 1 is an exterior angle. The angle that is adjacent to it is an interior angle, and the other two angles that are not adjacent to that exterior angle are called the remote interior angles. This PowerPoint will help us to see that demonstration. So exterior angles in triangles are angles formed by the extension of a side. And the remote interior angles are the non-adjacent interior angles to that exterior angle. Here's a triangle. If we extend to this side, we form this exterior angle. And these are the remote interior angles. If we extend a different side, this is our exterior angle, and now these two are the remote interior angles. Finally, if we extend this last side, this is our exterior angle, and these are our two remote interior angles. Now, I would like you to do an activity to help you see the relationship between the measure of the exterior angles and the measure of its remote interior angles. Okay, hopefully from your results you saw that the exterior angle is equal to the sum of the measures of its remote interior angles. I'm going to do a demonstration of a new kind of proof to prove this theorem, the exterior angle theorem, called a flow proof. In a flow proof, we have boxes with a statement and a reason inside of them. And then we have arrows coming out of those boxes leading to another box, which is a conclusion that we can make based on what is in the original box. So I'm going to start off by making a box. And typing the given information inside. So we're trying to prove in this picture here, we have triangle ABC and exterior angle 1. We're trying to prove that the measure of angle 1 is equal to the measures of its two remote interior angles, angle A plus angle B. So we'll start off with this triangle ABC. So in a flow proof, in the box, I write the statement that I have triangle ABC and the reason this is given information. Now, we recently learned that when I have a triangle, I know that the sum of the interior angles are 180. So the measure of angle A plus the measure of angle B plus the measure of angle 2 must be equal to 180 because of the triangle angle sum theorem. So I'm going to make an arrow coming out of that box because my next box will be a conclusion based on the fact that I have a triangle. I'll create another box and write my statement that the measure of angle A plus the measure of angle B plus the measure of angle 2 equals 180 degrees. And again, the reason I know this is because of the triangle angle sum theorem. Next, I'm going to make another box. This box actually comes from a conclusion from the picture and not from either of these statements. As I look in the picture, I notice that angle 1 and angle 2 form a linear pair. We know from the supplement theorem that when two angles form a linear pair, their measures add up to 180. Again, since this does not come from either of these statements, I'm going to make a box by itself with no arrow going into it. This time my statement is the measure of angle 2 plus the measure of angle 1 equals 180, and this is because of the supplement theorem. Now, notice I have two equations. Both are equal to 180. Remember that the transitive theorem, the transitive property, says if two things are equal to the same thing, then they are equal to each other. Since my next statement involves both of these statements, I'm going to have arrows coming both of these boxes to my next box. So this one says the measure of angle A plus the measure of angle B plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 1. And again, that is the transitive property. We also could have used substitution here by saying the measure of angle 2 plus the measure of angle 1 is substituted in for 180 in this equation. Either transitive or substitution are good reasons for this statement here. Alright, finally, from this statement, we have the measure of angle 2 on both sides of the equation. So we can subtract that because of the subtraction property of equality. It tells us that if we have the same thing on both sides of the equation, we can subtract that. So I will use this box to create my final statement, which says the measure of angle A plus the measure of angle B plus the measure of angle 2, measure of angle A plus measure of angle B equals the measure of angle 1, which is what we have left after we subtract the measure of angle 2 from both sides. So this reason is SPOE. Notice that was the thing that I was trying to prove, so my proof is finished. The nice thing about flow proofs is that I know exactly what statements I'm using to come to each conclusion. The hard thing about flow proofs is making sure that your arrows are completely correct, that I only have arrows coming from a box going to a different box if I use that original statement to make that conclusion. You'll be practicing flow proofs throughout class. Now I'd like to talk about a corollary. A corollary is a theorem, so it is a proven statement, but it's a statement that I don't need a long, elaborate proof to make, that it comes directly from one other theorem. The first corollary that we're going to look at is that the acute angles of a right triangle are complementary. This comes from the fact that the angles in a triangle, measures of the angles of a triangle add up to 180. If one angle is 90, the other two have to add up to 90 in order for all three to add up to 180. Two angles whose measures add up to 90 degrees are complementary. Another corollary is that there can be at most one right or one obtuse angle in a triangle. Again, this comes from the angle sum theorem that says the angles add up to 180. If an angle is 90 or more than 90, the other two angles can only add up to 90 or less than 90, and therefore individually have to measure less than 90 degrees. Now we're going to talk about what it means for shapes to be congruent. Remember, congruent means to have the same shape and size. When figures are congruent, all of their corresponding parts are congruent. For triangles, that means all 6 of their corresponding parts are congruent. All 3 of their corresponding angles and all 3 of their corresponding sides. Now we're going to talk about a congruence statement. A statement that says 2 polygons are congruent. When we say the 2 triangles are congruent, it does matter what order we write that statement in. When we name triangles, it doesn't matter if I call this triangle ABC, BCA, CAB, and so on. However, a triangle congruent statement must reflect the corresponding parts that are congruent. So if I decide to name this first triangle ABC, I have to name the second triangle in the same order of corresponding parts. Since angle A and angle H are congruent to each other, they must be in the same place in the congruent statement. Same thing for angle B and angle J, angle C and angle K. The segments also must be in the same order. AB and HJ are corresponding sides and are congruent, and therefore must be in the same place. BC and JK, AC and HK also. Notice if I called the first triangle BCA instead of ABC, the second triangle would have to be JKH instead of HJK in order for the parts to be in the same place. This is an incorrect triangle congruence statement because B and K are not corresponding parts, but they're in the same place in the triangle congruence statement. Finally, I want to go over one last theorem in these sections, the third angles theorem. This theorem also comes from the triangle angle sum theorem. And it says that if 2 sets of angles between 2 triangles are congruent, the third set must also be congruent. This makes sense because if these 2 are congruent, these 2 would have to be the same measure in order for both sets of angles to add up to 180 degrees.